let's continue on with some more terminology. The placebo effect, which we also kind of mentioned previously, it occurs when a subject receives no treatment but incorrectly believes they are in fact receiving the treatment and responds favorably. So this is like in a medical trial where you receive the fake treatment, you believe you're getting the treatment, so then you react favorably. This is actually why we have the treatment that we give is called a placebo, to try to determine are the results we're seeing because people think they're getting the treatment or because they're actually getting the treatment. This is why we don't just have a baseline that gets no treatment at all. We actually make them, we simulate that they're getting the treatment. This is different from the nocebo effect, which occurs when the person receives no treatment, but again, incorrectly believes that they are in fact receiving the treatment, and it means that then they respond negatively. So this might be something where someone, every time they get a shot, they seem to get sick. So they're so sure that every time they get a shot, they're going to get sick. So maybe the treatment is you give them a fake shot, it's nothing but saline, and then they get sick. So the placebo effect is when they think they got the treatment and they react favorably. The nocebo effect is when they receive the fake treatment and they respond negatively because of it. So patients in clinical trials who experience side effects from the placebo because they're told of the side effects of an active treatment, this might cause the nocebo effect. If you're told that we're giving you this new treatment, now some people have reported that they get headaches, dizziness, and nausea. Well, now you're on the lookout for headaches, dizziness, and nausea. So every time you get a headache, dizziness, or nausea, you suddenly are attributing it to the medication that you think you're receiving, but you're actually not. Whereas, and it might just be day-to-day life where you would have those things, but you wouldn't think anything of it because maybe the headache's really not that bad. It's just a minor headache. Maybe you got up a little too fast and you got a little dizzy. Where now you're associating it with those side effects because you were told about them. Patients will experience severe adverse effects from medicine due to widespread concerns about the medicine's safety. Now, this would be one where someone might have seen a lot of information that there's a lot of negative side effects to this medication, and so they're very sure they have a negative view of what the side effects will be and how bad they are, and so they'll react negatively even if, again, they receive the placebo. Or you might have patients who experience side effects from the brand change of medicine. So this would be something like when people claim that when they take this medicine, it works, but if they take this one, which is the exact same thing, but maybe it's a different brand, they react negatively. This could be an effect, be part of the nocebo effect. Now, a block is a group of individuals sharing some common feature that might affect a treatment. This could be things like gender, age, or something like has diabetes. Now, we talked about grouping people into groups based on using randomization so that we get the entire sample and we randomize into the treatment group and the control group. Well, we also will sometimes use what's called blocking, where we first set individuals based on this block. This might be something like has diabetes, does not have diabetes. And then within each of those blocks, we then will have a treatment group and a control group. And within the other block, you'll have a treatment group and a control group. So this is an example on the slide here of a blocking experiment. So you have all your subjects, and we've divided it into those who are 30 to 39 years old, 40 to 49 years old, and those who are over 50 years old. Because let's say in this experiment, you believe that the age may impact how people react to your treatment. So the 30 to 39-year-olds have a control and a treatment. The 40 to 49-year-olds are split into a control and a treatment group. And the over 50-year-olds are split into a control and a treatment group. So now you have these blocks, and within each block, you have a control group and a treatment group. So you can see, does the treatment seem to work based on the different blocks? So I mentioned before, like people have diabetes. This might be something where you first want to separate people by those with diabetes and those without diabetes, because that might actually impact how people react to a treatment. Maybe those without diabetes, you have your control group and your treatment group, and the treatment group does seem to have really positive results. Maybe those with diabetes do not have the same results when you compare the treatment with the control. And it might be that for some reason that block that has diabetes factor is actually affecting how they're reacting to your treatment. We have matched pair design. So another type of experimental design is called matched pairs design, in which subjects are paired up according to similarity. So one of the subjects in each pair is randomly selected to receive one treatment while the other subject receives a different treatment. So in this case, you're comparing one to one, right? So if, for example, let's say we had people of different ages, we might choose the youngest two who are about the same age, similar people, so that they kind of are matched together. So for instance, two subjects may be paired up because of their age, geographic location, or particular physical characteristics. A complete random experiment is one in which a random process is used to assign each individual to one of our treatments. Now notice in this one, I say one of our treatments, because up until now, I've been talking about treatment group and control group. But you actually could have more than one treatment going on at one time. You could have treatment group 1, treatment group 2, and control group, or something like this. This might be something like if we wanted to see how vitamin C affects somebody's recovery from some sickness. Every person here in this study will be dealing with the sickness. Well, treatment A might be that we're going to administer vitamin C through a liquid supplement. Maybe treatment group 2 is also getting vitamin C, but they're getting it through a physical tablet that they take. And the treatment group, or the control group, is getting no treatment. They're just getting either, a tablet or a liquid supplement, but it's actually not a supplement, it's just a fake one. And then we can actually we can compare multiple treatment groups and the control. Now, complete random experiment means that everybody was randomly assigned with no rhyme or reason to why they were selected in that group. Usually we use a computer for this. We just do a random assign where everybody has an equal likelihood of being selected, and then they end up in one of those groups, treatment 1, treatment 2, or control. A randomized block experiment is individuals are first sorted into their blocks, and then they're randomly assigned to each of their groups. So this would be something like you've got all of your people in your sample. So this is your original sample. And then you're going to split them up like in that one image we did. So this is going to be block 1, and this is going to be block 2. And then from there, we would split them into, let's call this treatment 1, treatment 2, and control. And then this group also is going to be split into treatment 1, treatment 2, and control. So in this case, this would be a randomized block experiment because we first begin with this blocking phase where based on some condition that we think may affect the treatment. Then within block 1, we would then split them randomly into treatment 1, treatment 2, or control, or however many treatments we have. Block 2, we also would randomly split them between treatment 1, treatment 2, and control. Blinding helps us control or minimize the placebo effect. Now, there's two types of blind experiments. The first is a single blind experiment. This is an experiment in which the subjects alone do not know which treatment they are receiving, right? So for example, with this current example here, this person does not know whether they're getting treatment 1 or 2 or control. This one does not know if they're getting treatment 1 or 2 or control, and this group does not know if they're getting treatment 1, 2, or control. But the person who's administering the treatment does know which one they're getting. Now, a double-blind experiment is an experiment in which neither the subjects nor the people who are working with them, the people giving them the treatment, know whether they're in a treatment group or the control group. So the experimenter is informed after all the data has been collected, and the type of experimental design is preferred by researchers. Now you might wonder, why do we not want the researcher or the one person administering the treatment or the placebo to know? And this is because, remember, we always want to try to find any way that we can limit bias. So going back to a previous example I did, let's say that you're doing a medical trial and you are dealing with some condition which is terminal, meaning that everybody in this subject group has some terminal disease. And you are testing out some treatment which has had a lot of positive results and you think it really could be the cure for this. Well, if you're the person administering the drug, you know that one group is getting it, so you're excited. You're like, these people, I'm saving their lives. I'm helping these people live a better and full life. And you're happy about it. You're more upbeat, you're smiling, you're joking with them as you give it to them. Then you go to the control group. And this is a group of people who have a terminal illness, and you're giving them basically a sugar pill. How do you think that would affect you as somebody administering the fake treatment? You know that you are not helping them. They have hope that they are receiving the treatment, and they're part of the treatment group. And you basically are giving them false hope. So basically, by doing that, when you're giving them that fake treatment, you actually would have different mannerisms, right? You're only human. You might be, less upbeat, less joking with them. Maybe your small hints you're giving, even if you don't mean to. You try to, put on your game face, be stoic about it. But in the end, humans are not good at hiding our emotions. So we use a double-blind study so that even the person administering the treatment does not know whether they are giving the treatment or whether they are giving the placebo. Now, another effect, this one's not really one we test on, but I think is interesting, is called the Hawthorne Effect. So the Hawthorne Effect occurs in an experiment when subjects change their behavior simply because they know they're participating in an experiment. So some examples of this would be, think about like anyone who's looked at like online dating, right? You go on and everybody seems to be really big into running and outdoor activities when, let's be real, most of us aren't nearly as active as we should be. But we like to put our best foot forward. The same thing happens in experiments, right? If I sign up for a study with the psychology department, guess what? I know I am taking part in a psychology experiment. So if I'm in a room and they're giving me a test, and maybe the person walks out of the test room and I see the answers sitting there on the table. Well, under normal circumstances, maybe I might be tempted to say, okay, well, the answers are right there and I'm getting a pretty big payout if I do well in this test. I'm just gonna, glance at the answers. I'm not usually a cheater, but that's a lot of money. But you think to yourself, well, I'm in a psychology experiment. So you start looking around. You know that there's probably cameras somewhere. You know that this is actually probably the treatment. Right? You think the test is the treatment, but it's actually to see how much people are willing to cheat. And in fact, this is something that has been done, these kind of experiments. What they'll do is they'll have people work in groups, but you don't know that the person working with you is actually part of the experiment, and they will try to convince you to cheat. You think that the test, whatever they're testing you on, is the treatment, but they're actually trying to see whether you will one, look at the results, and whether you will then stick with telling them the truth or not. They have a camera. They know what you're doing. But the Hawthorne effect is when you change your behavior because you know that you're part of an experimental group, right? So this isn't some random thing. You're not in a room with random people. You know you signed up for a psychology experiment. So now you're looking at everything. Every mirror you think might be a one-way mirror where they're watching you and they're observing you. You're looking around for cameras. You're trying to act a certain way because, let's be real, as humans, we generally, again, want to put our best foot forward. Okay, so now, enough information. This is the easiest way to reduce the margin of error. And the easiest way to reduce the margin of error is to increase our sample size. So remember before we talked about error. Error is just how far off our sample estimate is, our statistic, from the population parameter, the actual value. Now, the best way to try to limit that error is to just get a bigger sample, because what's going to happen is more likely I will have a more representative sample. If I have 1,000 people in my population and I take a sample of 10, chances are, even if I randomize it, they're not going to be that representative of the population. Now, what if it was 100 people? Okay, that's 10% of the population. That's probably pretty representative. Well, what if my sample was 999 people out of 1,000? Well, that's probably very representative of the population because it's almost the entire population. So the easiest way to reduce your margin of error is just increase your sample size. And we will talk more about this whenever we're actually doing different calculations later in like chapter 5 and things like that. Validity. The validity of an experiment refers to the accuracy and reliability of the experimental results. So we talked about this. Just because you get results doesn't necessarily mean that they're very reliable. So the results of a valid experiment are more likely to be accepted by the scientific community. Just because you did a study and you get results, it doesn't mean that it's going to be accepted. But if you did a really good study where you limited bias, you got in a big enough sample size, you made sure it was representative, you had your control, these are all things to help people accept the results. So to improve the validity of experimental results, replication is actually probably one of the best ways, because even if I do everything right, like we've talked about, I may get results which are not correct just because of the randomness of how I selected my participants and my sample and all that kind of stuff. But if I replicate the study, this helps strengthen the case that I do have a valid study. Okay, now we have sample size. So sample size is just the number of subjects in a study. So sample size is simply written as little n. So sample size is, we write it as little n or lowercase n. This is a subset of our population, which if you remember from earlier, our population size we write as capital N. So this should be as representative as possible. So you want this sample, your size of your sample, to give you enough people so that you can get a representative sample of that population. Now, let's talk about sampling frame. Sampling frame is a list of elements belonging to our population from which the sample can be drawn. Now, you might wonder, why do we have a sampling frame, right? Because we're taking a sample, which is a subset of the population. The problem is, just because somebody's part of the population doesn't mean that they're actually accessible to be part of your sample. An example of this might be, if you want to do a study where you physically need to be with people to do something, I have no way that I could ever do this with somebody who's currently serving on the International Space Station, or someone who's in the Navy who is currently at sea in a submarine, or even on a ship. I may not have access to people who are imprisoned, or maybe on death row, or something like that. Just because somebody's part of the population, right, those are all Americans, let's say, it doesn't mean that I have access to them. So your sample frame are those that you can actually sample from your population to create your sample. So while your population may be 1 million people, your sample frame might be only 950,000, because those other 50,000 are just not accessible to you no matter what you want, no matter how much you want them to be a part of your population to sample from, they're not available to you. So they're not part of your sampling frame. So next we have our sample design. This is the process of selecting sample elements from our sample frame. So we are going to be actually talking in depth about the different ways that we can sample from our sampling frame. Now, a couple more definitions before we get to our different methods of sampling. The first is a census is a count or measure of our entire population. Now, we talked about this before. Taking a census provides you complete information, but it's often very costly and difficult to perform. Now, when we take a census, we have a parameter, right, that represents the population variable that we're interested in. Well, the population parameter, we often refer to as the true parameter, the true value. So if I take the average GPA of all USF students, then I know what the average GPA is. It's the true average GPA because every USF student was taken into account. Now, sampling is a count or measure of part of our population, which is more commonly used in statistical studies, which is, again, remember, when we get some information about that sample, we call it a statistic. The field is called statistics because that's what we focus on, is those subgroups of the population that we're actually studying. Now remember, our error is how far off our estimates are from the true value. So that true value exists, right? There is an actual average GPA of all USF students. If I have 300 students, though, that I'm using, I'm going to have some amount of error, right? I'm trying to say what the population average GPA is, but in the end, I know that there is some GPA and there's some amount of error. I may not know what that error is. I might be very close. I might be a little further away, but I do know that some error exists. And that's really kind of what sets statistics apart from mathematics. Statistics is basically mathematics with randomness and error involved. It has that unknown factor to it. So even if you do everything right, there will always be that we're 95% confident this is correct. We are, we can say this with 5% level of significance, and all this will make sense when we get later on. So to collect unbiased data, a researcher must ensure that the sample is representative of the population. So an appropriate sampling technique must be used to ensure that the inferences about the population are valid. So remember that when a study is done with faulty data, the results are going to be questionable, right? So my focus is I do statistical and machine learning. So we have a phrase for this, which is garbage in, garbage out. right? It doesn't matter how good your algorithm is. It doesn't matter how well you set up your model. If you have bad data, you're going to get bad results. So if you have faulty data, your results aren't going to be very reliable. Okay? So even with the best methods of sampling, a sampling error still may occur, right? This is what I talked about previously. You can take all the right steps and still get a bad sample, right? And you'll learn all about this in chapter 3 when we're talking about randomness and probability, that sometimes it happens. If I flip a coin 20 times, chances of me getting 20 heads is very small, but it is possible. And you don't know that when you did your experiment, maybe your experiment was the 20 heads example, the very tiny, minute probability of that occurring, and yet that was the sample that you happened to get for that one. So sampling error is, again, the difference between the results of our sample from those of the population. Now, we don't know what our sampling error is. We just know that there is some sampling error. We know that there is some true parameter value, and we get our value. Now, we don't know how big that error is, but we do know that our value has some amount of error from that true parameter. So when you learn about inferential statistics, you're going to learn techniques for controlling that sampling error. Or in worst case, a lot of times what we do is we take the worst case scenario, which is based on our data. If this is what we think the error is, we'll just kind of take a worst case and we'll say it's probably this, and therefore we're likely to have actually caught whatever it is we're looking for. And again, you'll learn all about that when we're doing chapter 6 and chapter 7. Okay. So when we come back in the next video, we will be looking at those actual sampling techniques that we talked about. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.